as I said I would do. We can take 5 minutes if there's any residual questions associated with the chapter 5 stuff. Any more questions that you found or circuits that you need help with? The test, as I said, 32 multiple choice, 7 written response, 32 in part 1, 35 in part 2. It's out of 67. Yeah. Be able to explain it?
Yeah.
Not really. You just have to know that because Einstein explained it using Planck's quantum theory, it gave credence to the quantum theory.
Okay.
Yeah, but no, you don't have to like imagine bowling pins on the edge of it. No, you're not for.
Okay.
Yep.
When calculating for percent abundances, how do I know how many sig figs to run into?
Go to 2 decimal places.
Oh.
Yeah, and I'll probably remind you of that. And that's true for probably for both types of calculation. Yeah. Yep.
You have to know how to do most and least deflection.
Probably because, I mean, the deflection is based on the charge to mass ratio. So all that is whatever heaviest is getting deflected the least. That's all you have to know. Because in the spectrometer, they usually have the same charge. So the E is the same. So the only thing determining deflection is the M. The bigger the M, the heavier it is, the less it's deflected. Like a golf ball going through a crosswind as opposed to a ping pong. Okay. Okay, let's move on to chapter 6. I know we got short blocks today, but for all intents and purposes, I'm going to finish 6-1 if I can. Right? Now, because I mentioned this before, number 1 in the warm-up should probably be more correctly worded. Can you remember the meaning of the word periodic? Periodically. What does that word mean? Think back, it was September. It seemed like a long time ago. Remember how stupid you were at September? You knew nothing about stoichiometry, nothing about multi-step conversion. Nothing about
regularly reoccurring something.
And now you're enlightened. So you could be forgiven for forgetting what we talked about in September. You remember the name. The word periodic means regularly repeating. And anytime we say that term, the periodic table, the name of one guy normally should spring instantly to mind.
Right.
Born in the forests of Siberia, Russian chemist named Dmitry Ivanovich Mendeleev. Okay. Now in chapter 5, we went through several names that were kind of important that you kind of have to remember. Major contributions to our understanding of the atom. I mentioned a few names at the beginning of chapter 6 too, but you don't have to remember them. The only one you have to remember is Dmitry Mendeleev. Okay? Science in general and chemistry in particular exists because our human species has always had an insatiable desire to make sense out of the world that we sought for phenomena. To solve the mysteries, to discover the order and logic, and deciphering the events and objects we encounter. One of the most important, and as far as I'm concerned, the most important and successful examples of such efforts is the development of the periodic table of the elements. This single document is arguably more valuable to us and perhaps even society itself than any piece of equipment, wonder drug, or process ever invented. That thing makes sense out of every form of matter in the universe. And one of the most amazing things about it is it was constructed effectively in its current form before we had any idea about atomic structure. So the order that we've discovered in terms of the elements' property or behavior was all experimental. But that was 50 years before quantum mechanics was ever developed. Once quantum mechanics was worked out, all it did was confirm everything in the periodic table. We didn't, in other words, develop quantum mechanics and then have to go to the table and go, now we're going to have to change this. We didn't have to change anything. It's one of the best marriages of theory and experiment that I'm aware of. And you can be sure that anybody that does chemistry for a living has one of those within eyesight. If you knew everything associated with the organization of the elements and periodic table, if you knew what all of that meant, you could teach any chemistry course at any level, anywhere in the world. And there are chemists who spend their careers doing research just on that thing, learning what we can about the elements relative to each other based on where they are relative to each other. The table had its beginnings in the early part of the 1800s. By 1872, the number of elements were kind of rapidly being added. A few elements were known in ancient times, but in 1800, Alessandro Volta invented the electric battery. What it gave society then a tool in the form of a steady flow of electric current, which could then be used to chemically pull apart compounds into their elements. And that's electrolysis. And we actually used that when we talked about relative mass. So for example, if you've got magnesium oxide and you pull it apart, well, how do you pull it apart? If you can pull compounds apart into their elements, you likely are going to, discover new elements. And with that rapidly increasing number of elements, there almost became an immediate need to organize them in some meaningful fashion. German scientist Dobereiner, you have to remember his name, noticed similarities within several groups of three elements. And one of the ones that he noted were chlorine, bromine, and iodine. He called them triads. He didn't do much with it after that, but the fact that there were similarities among the elements suggested that maybe some sort of organizational scheme was possible. In 1857, English chemist Olding proposed that the elements could be divided into groups based on their chemical and physical properties. Yeah, correct. Many of those groups actually resemble the vertical columns in the table today. In 1862, a French geologist named André-Émile de Chantertois arranged the elements by increasing atomic mass. And he noted that the elements with similar properties seemed to occur at regular intervals. Yeah, that was important. He devised a spiral graph with the elements arranged onto a cylinder. So it was an interesting way of demonstrating it. And then he sort of had the elements by order of increasing atomic mass going up like this. And the way he envisioned it was, by the time you went all the way around this one, you get to a place here where this element has similar properties to that one. Interesting way of doing it. But the paper he published, though, was largely ignored by chemists for a couple of reasons. He left out the graph when he published his paper, which is kind of the whole point. It was very difficult for chemists to envision what it was he was talking about. Moreover, he was a geologist, so he didn't write it from a chemist perspective. And so it was pretty much ignored, but he was on the right track. A couple of years later, an English chemist named John Newlands noticed that similar properties seem to repeat every 8 elements, much the same way that notes on a musical scale repeat every 8th tone. Do, re, mi, fa, sol, la, ti, do. Newlands called this the law of octaves, for obvious reasons. You don't have to remember any of those guys' names. The most successful organization of the elements, though, was arrived at independently, and as the story goes, almost at the same time. A German chemist named Julius Lothar Meyer and Russian chemist Dmitry Mendeleev both formulated a version of the table, okay? In a paper submitted to the Russian Chemical Society in March 1869, Mendeleev arranged the elements into what he called the periodic table. He called it that because he proposed the periodic law. And the 1869 version of the periodic law reads like this. If elements are arranged in the order of increasing atomic mass, A pattern can be seen in which similar properties recur on a regular or periodic basis. That's the answer to the question, what does the word periodic mean? The only thing we've changed in the periodic law since then is this one. Table was eventually rearranged in order of increasing atomic number, and we'll get to that soon. Notice that this is called a law, not a theory. It's not called the periodic theory. Theories attempt to explain why relationships, regularities, phenomena exist, whereas laws simply tell us that they exist. They identify. We'll see if we can supply a why by the end of this section, and you already know the why. Dmitri Mendeleev received most of the credit for several reasons. The most obvious one is that he publishes a year before mine. Even though, as the story goes, they arrived at the same thing at about the same time, Meyer, for some reason, took a year to publish it. So Mendeleev was before him. Secondly, Meyer chose to focus on physical similarities, physical properties that were similar. Mendeleev said, no, I think it's more important to focus on the chemical properties, how they behave chemically. But arguably one of the most important reasons that Mendeleev's was accepted compared to Meyer's was that Mendeleev left blank spaces in his table. So what did he do? He took little filing cards, the same ones you might write for yourself, flashcards if you're studying, or if you're doing a speech contest and you have those little memory cards. He wrote everything he knew about all of the elements that existed in 1869, and he tacked them up on a bulletin board in order of increasing atomic mass. And he noticed at regular intervals, not identical, but similar properties occurred. Okay, and he took those similar elements and he put them underneath each other. But every once in a while, he came to a place where there should be an element based on its properties, but there wasn't one. And so he said, okay, well, maybe that means we haven't discovered all the elements yet. So he took that blank space and he plunked it in where the element should go when it is discovered. But based on where that blank space was, and based on the properties of the element above it and below, he said, okay, when it is discovered, it's going to have these properties. This is his second version of the table in 1872. We'll talk about it in more detail in a second. But he left 4 blank spaces in this table: 44, 68, 72, and 100. So, for example, here's 72. Just to show you how correct his organization must have been. In 1871, he predicted that an element would be discovered with that mass. And with that density, very high melting point, with that specific heat, remember that from science, the amount of energy it takes to raise 1 gram of material 1 degree Celsius. That formula of its oxide, the R, is just how back then we represented generic element symbol. A 1-to-2 ratio with oxygen, that should be the oxide density, that should be its chloride formula. 15 years later, germanium was discovered. That's its mass, that's its density, very high melting point. That's its specific heat, exactly. That's its oxide formula, that's its density, exactly. That's its chloride formula. That's when scientists pay attention to stuff. When something can be predicted correctly years ahead of time. Because this was a revolutionary idea, the periodic law, as is often the case in science, it wasn't instantly accepted. It was gradually accepted over time. And remember, when Mendeleev proposed the periodic law, 1869, that was 30 years almost before the electron system. As far as Mendeleev was concerned, atoms were like tiny little indivisible billiard balls. So there was no notion of electrons, no notion of charge, no notion of protons, valence shells, none of it. All his organization was based on was experimentation. Now, obviously, this looks a lot different than that. We know we have discovered and synthesized a lot more elements than existed back in 1872. But there are some similarities. So here are the groups. We've got 8 groups. You notice there's more than 8 groups in the table now. But the 8 groups that he has here and what's in them is pretty similar to these 8. And remember what those 2 blocks are, the S and the P. And S and P are always on the outside. Mendeleev had no idea what was there. He was just basing it on how they behave chemically. So what he called Groupo 1, this symbol is that's what the formulas of all of their oxides were. A 2-to-1 ratio with oxygen. That little 2 looks like a square, but it's back then that's how we wrote a formula instead of a subscript. In group 2, a 1-to-1 ratio with oxygen. In group 3, a 2-to-3, etc. This is the formula of the hydrides. 4-to-1 ratio, 3-to-1, 1-to-1. So let's look at some similarities and differences. So notice in group 1, lithium, sodium, potassium, rubidium, cesium. Lithium, sodium, potassium, rubidium, cesium. Now he's got other stuff here. Those are the most reactive metals in the table. But he's got 3 others that represent among the least reactive metals in the table. Copper, gold, and silver. Why would those be here? Well, they all form 1+ ions. Copper and gold don't only form 1+ ions, but they form 1+ ions, just like the alkali metals, which means the formulas of their oxides are going to be 2-to-1. Silver only forms a 1+ ion. So in terms of like reaction rate, no. But in terms of chemical properties, formulas, yes. Group 2, beryllium, magnesium, calcium, strontium. This is the old symbol for barium. Beryllium, magnesium, calcium, strontium, barium. What else is he got? Well, he's got zinc and cadmium and mercury. Why? Well, they all form 2+ cadmium. Again, that's what he's basing it, which means the formulas of their oxide should be listed. So the intent here is not that you match that to that exactly. You can't. But there's a lot of similarities to it. And the reason for the similarities are based on chemical behavior. Okay? Because of its obvious usefulness, I know the periodic table gained widespread acceptance. We should remember, though, that the periodic table, first 1869 and 1872, was constructed prior to any discoveries about the inner structure of the atom. Similarities of various elements were eventually explained based on the fundamental description of electron arrangements, but the table identified those regularities more than 50 years before they were understood. Quantum mechanics is the Y part. The periodic law is the what point, and they married each other perfectly. If we skip ahead now to modern times, since its creation, the periodic table has undergone several changes. Obviously, many new elements have been discovered or synthesized since 1872. But the most significant modification occurred in 1913, and I'll refer to this in a few minutes. Data gathered by the young British chemist Henry Moseley, combined with the discovery of isotopes, resulted in the elements of the table being reordered according to their atomic numbers. So this is the modern version of the periodic law, modern courtesy of 1915. Instead of mass, we had number. Because now we know what defines an element: positive charge in the nucleus, the number of protons. And that meant that several pairs of elements had to be rearranged. And An obvious example of that would be argon. If you arrange the elements strictly in order of increasing atomic mass, argon is actually compared to potassium. Potassium is lighter than argon. Okay. Argon is heavier than potassium, so in order of increasing atomic mass, potassium should go here, argon should go here, which makes no sense at all chemically. Because number one, argon's a gas, even though it's solvents. Also, it's an unreactive element. These are the most reactive metals in the table. But if you arrange them in order of increasing atomic number, even though potassium is lighter than argon, it fits here, and argon fits there. Okay. Now, this guy's name, interesting in the trivia, you're not going to hear Henry Moseley's name probably again. You may not even hear his name mentioned in any chemistry text going forward. Brilliant chemist, young man. But he signed up for the British infantry when the outbreak of World War I occurred. And very soon thereafter, he got shot through the head by a Turkish sniper and died. So had he not been killed, you could argue that he probably would have contributed a lot to chemistry or science. The British government, that tragedy wasn't lost on them, and shortly thereafter they enacted a law. I'm not sure what the name of it is, but basically it says if you're a brilliant young scientist, you can't sign up to get shot in the infantry. You're not allowed to get shot. Okay, so we want to save your brain. So they put brilliant people to work doing other things in the war effort rather than, here's a rifle, good luck. And a great example of that is The Imitation Game. You guys saw that movie? You haven't seen that movie? That's a war movie. It's a great movie. Got an Academy Award. It's about Bletchley Park in England, where the British government got the smartest Allied scientists they could find shortly after the outbreak of World War II, and they took them to this effectively castle in Bletchley Park, and they were code breakers. And they had a job, break the Enigma code. The German U-boats were destroying freighters, merchant ships carrying munitions and supplies to Britain from North America, and the German U-boats were sinking. And the way the German U-boats communicated with the high command and each other was through a little device called an Enigma machine. And what the Bletchley Park scientists did is their job was to break that code. And that the story is about the premier scientist in that group. Sad story on one hand, but it's a cool story. So I'm not going to tell you what happened. But the guy I'm referring to is Alan Turing. And he actually had to break the Enigma code. He had to build the first computer. And it broke the code. And you could argue, were it not for that, Britain wouldn't have been part of the victors. They would have lost the war. So yeah, if you ever get a chance to, I'm sure it's on pay-per-view, I'm sure. Imitation Game. And the star of that movie is probably somebody you've seen in other movies, Benedict Cumberbatch. He plays Alan Turing. Yeah, great movie. Anyway, I digress. So that wouldn't have happened were it not for Henry Moseley getting shot through the head. With the inclusion of elements 117 in April 2010, the periodic table now includes 118 elements. So up until 2010, it wasn't complete. There were blank spaces. It took a while for the UN of Chemistry, IUPAC, International Union of Pure and Applied Chemistry, to actually decide on the names for elements 113 to 118. But they did that in 2017, which means this sentence is no longer applicable. And since 2018, I have told Lionel, please take that sentence out of what I wrote because it no longer applies. He clearly forgot about it. So that no longer applies. We have named formally all the elements in the table. What IUPAC does when new elements are synthesized, nothing bigger than 92 exists naturally, as I've said. IUPAC, because it's a worldwide competition, who's going to synthesize the next element? And oftentimes there's a disagreement in who purports to have done what and when. So what IUPAC has to do is investigate the data. Look at the data from the researchers, from the laboratory that supposedly synthesized element A. And a lot of times there's disagreement. One group might say, well, we did it first, we did it here. And another group is going to say, no, here's our data, we did it here. So it wasn't until 2017, I think April of 2017, that IUPAC finally said, okay, these are the labs that actually did it. First, they give the researchers the honor of then picking the name of the element and then assigning its two-letter designation. Up until that time, 113 through 118 had 3 letters, which meant that IUPAC was fairly complete. So it's in your lifetime that thing has been completed. Now, could it be that there are new elements synthesized beyond what we have here? Yeah, but there's no spaces in what's beyond here. So this right now is the biggest element, but it's synthetic. It doesn't exist naturally. That's the biggest naturally occurring element anywhere in the universe. Beyond that, they're unstable. Now, there is even some ones that are unstable smaller than that. And what that means usually is that and it's kind of a different way of making it. There's an unhealthy or an unstable set of proton versus neutron numbers that just make some elements just unstable. And a good example of that is technetium. I think this was the first element that was synthesized. We believe that it existed somewhere in the Earth's crust long ago, but it's hard to do it to that last year. So I believe this was the first synthetic element. Basically, our protons take on the molybdenum, and we make technetium. We do that on purpose because we use that, for example, as a radioisotope to detect cancer. Okay. This one, promethium-61, we also think that existed at some point. But it was first discovered at ground zero when they detonated the first atomic bomb in the Mexican desert. So they named it after the Greek god of fire, Prometheus. So, but anything bigger than uranium never existed. We had to make it. And that's why you see those little radioactive symbols after everything all the way up to 118. But most of those things aren't around long enough to even measure their properties. They disappear in a fraction of a second. So we're not going to concern ourselves too much with those. We're going to focus on normally what exists naturally. We know that the periodic table has vertical columns or families or groups, and horizontal rows called period. Every element is a member of both a family and a period. So we can identify every element in the table, much like we can identify any location on a map by giving its longitude and latitude coordinates. So for example, an element that's part of group number 2, period number 4, that's one element. It's not unambiguous. Now, the older way of naming the vertical columns had A and B group elements. Some older teachers prefer that. I don't know of too many teachers older than me, but most teachers are familiar with what IUPAC has adopted as their way of naming the families, and they're just consecutive 1 through 18. But just to make older teachers happier, I put in the A and B group elements here. You might see some old periodic tables in some of your reference books that still have that, but IUPAC is from 1 through 18. That's how we number the groups. We number the periods 1 through 7, top to bottom. And you'll notice in your periodic table, they are numbered exactly that way, 1 through 7. The biggest distinction we can make in the periodic table is metals and non-metals. And we'll talk about that. And we referred to it way back in chapter 1 or chapter 2. But probably what we should say at the outset are the two most important things about the periodic table. This is section 6.1, effectively. That's the most important thing to know about this periodic table. Elements in the same chemical family have similar chemical properties because they have similar outer electron arrangements. You know that, right? Similar outer electron arrangements is valence shell. And invalence chemistry is chemistry. That dictates behavior. Okay? And because S and P are always on the outside, we normally refer to those two groups of elements as the representative elements, representative of their chemical properties, right? Now, you may not have heard them called a group of representatives. That's what they are. The S block and a P block collectively. Elements in families 3 through 12, those are referred to as the transition metals. They behave differently than the main group elements, and you should already be able to guess why. Within the transition metal elements are two horizontal series collectively called the inner transition metals. The first series, known as the lanthanides, goes from 56 to 72, and the second, known as the actinides, go from 89 to 103. Okay? And this is normally referred to as the short form of the periodic table. The long form would be if we plunked all of these in here, and if we plunked all of these in here. And if we did that, you don't often see this in a book because there wouldn't be room to diagram it. But there's the long form of the periodic table. And therein, you clearly see the four blocks: the S, the F, the D, and P. Okay, but the valence chains, okay, 2 here, 6 there, 8. The most general or division we can make in the table, as I said before, metals and non-metals, and we referred to this page back in chapter 2, I think. Almost 3/4 of the elements are metals, including some main group elements and all of the transition and intertransition metals. What do I mean by some main groups? Those are the S, all of the S, and some of the P. The first 6 bullets are physical properties. They're related to each other, but the 7th bullet is a chemical property. In taking part in chemical reactions, metals tend to give electrons away. They don't hold on to their electrons well. And that actually explains some of the physical properties. Non-metals, there are far fewer non-metals than there are metals. The first 3 bullets are physical properties. The last one is a chemical property. Non-metals don't give away electrons. They don't form cations. They either gain them if they react with other metals, or they share them if they react with other non-metals, suggesting that they would prefer to have more electrons rather than fewer. Along the staircase line are metalloids or semi-metals. And you'll notice that that zigzag line doesn't keep zigzagging. It doesn't go like that. It goes straight down after chlorine, which is why astatine isn't metal. I mentioned that because Gary said it was. It's not. Why do we call them metalloids? They're conductive, just like the metals. The fact that they're right between the metals and the non-metals is why some designations call them semi-metals. Metalloids, I think, is a modern term, but they're conductive, just like metals. But the reason we don't call them metals is because how their conductivity changes with temperature is different. With the metal, as the temperature goes up, the conductivity goes down. But with a metalloid, as the temperature goes up, the conductivity goes up. So that's the reason. And the metalloids are boron, silicon, germanium, arsenic, antimony, tellurium, and polonium, not astatine. Astatine's a bona fide halogen. It's a non-metal. As we move left to right across a period, or sorry, right to left across a period, elements get more metallic. More metallic means that they demonstrate these properties more. As we move top to bottom, they also get more metallic, which means the most metallic elements, if they get more metallic right to left and more metallic top to bottom, the most metallic elements are lowermost left, meaning they want to give away electrons the most. The least metallic elements are upper right. And we're going to ignore the noble gases because they don't react. So based on that, the most metallic element should be francium, which is also radioactive. The least metallic element should be fluorine. And if metals tend to give away electrons, the element in the table that wants to give electrons away more than anything should be francium. And the element that wants to gain electrons more than anything should be fluorine. And they are. This is a grade 10 exercise. That's just navigating the table. So based on what I just said, what about 2A? Rearrange the following alphabetical list in order of least metallic, and if you want to write in brackets above that, uppermost right, the most metallic, in brackets, lowermost left. That's all you need to know. They're listed alphabetically. So if you want to do the bookends of that, whatever's lowermost left on the table is the last one on the list. That would be most metallic. Whatever is uppermost right would be least metallic. That would be the first one. So based on that, the first one should be fluorine. And in that list, the last one should be cesium. Cesium is the most non-radioactive, the most metallic, non-radioactive. Francium is radioactive, but cesium isn't. And then the rest, basically you're doing this. If you're going from least metallic to most metallic, you're doing this. Whatever's lower down on the left is more metallic. Whatever's upper more on the right is less metallic. And we already answered B. Based on your answer to A above, which of the 8 elements listed would you expect to have the greatest tendency to gain an electron? The least metallic. Fluorine. Greatest tendency to lose an electron. In the list, cesium. And as we've done before in younger grades, I'm pretty sure we did it in grade 10. It's the number and type of outermost electrons that are primarily responsible for an atom's chemistry. We know that members of a chemical family have similar numbers and types of outermost electrons. In grade 10, we just said, well, they have the same number of valence electrons. But if we apply quantum mechanics, it's not just the same number. It's the same number of electrons in the same orbital. So we've talked about alkali metals before. They're the elements on the far left. Physically, they're all soft, silvery solids. They can all be cut with a knife or a pair of scissors. They're the most reactive metals. One of the things they do is they react violently with water and produce hydrogen gas in an exothermic reaction. And if the reaction is fast enough, the hydrogen ignites. If you write their electron configurations from top to bottom in core notation, the similarity becomes immediately obvious. They're all S1. And this is the one electron that's given away. So the similarity is obvious. But what's changing as we go down? So this could be core notation NS1, N meaning What do we call N? What's the name we give to that first quantum number? You know the name? Principal quantum number. What does it tell us?
Relative size.
Size of the charge cloud. So what's changing as we're going down? The atoms are getting bigger. That's the second most important thing to know about the table. As we go down a family or across a period, there's regular and predictable changes in these properties, in their chemical properties. We call those periodic trends. And that's section 6.2. So we said that francium was the element that wanted to give away electrons more than anything. Well, let's ignore the fact that it's radioactive. Why would that be? All the alkali metals love to give electrons away. But why would francium give it away the easiest?
It's also the biggest.
We're giving away an electron that's only there because it's attracted by a nucleus, right? How many electron clouds does that 7s electron have to see through to feel the nuclear pull? 6. There's 6 electron clouds between this and the nucleus. Obviously, the nucleus of francium is stronger than the nucleus of cesium. But that outer electron is seeing through a whole extra cloud of negative charge. And that doesn't just get in the way of the nucleus, it also repels that 7s electron. And we're going to talk about that in section 6.2. So as we go down, atoms get bigger. And as they get bigger, that dictates things, dictates a lot of their behavior. Okay? It might surprise you to know that as we go left to right and add protons and add electrons, you might initially expect atoms to get bigger. They don't, they get smaller. And I'll explain that probably after you guys get back from retreat, because I can use retreat as an analogy. All right. I've mentioned here that all the alkali metals react vigorously with water to produce flammable hydrogen gas and actually hydroxide compound. I did this for the other classes, so I thought, why not? I'll do it for you guys too. Search this on YouTube. Get the links in a second. What these guys do is they take a couple alkali metals. If I took a little fingernail's worth of lithium, threw it in a glass of water, all the alkali metals are really light, so they all float on water. Lithium gives away electrons, reacts with water, produce hydrogen gas, but it doesn't do it so fast that it's dangerous. You might see a little bit of a spark. If you take sodium, you will see some sparks as the hydrogen gas is ignited because the reaction is faster. Potassium starts to get a little scary. With the same amount of rubidium, and especially cesium, it's not just a combustion, it's a detonation. So they show you quickly potassium and maybe sodium, but then they demonstrate rubidium and cesium. You gotta live through this ad. You gotta get me one of those. Go ahead. Yep.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. The odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Right, I'm off. Have
So
that.
they're not gonna put it in
Okay.
glass water, they're gonna put it back.
Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone.
Well, it still looks like a bathtub.
Yes. That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There's one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly in our feet, could go up at any time.
That's it.
Oh, yes.
I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave it for you.
Thank you.
Hey, John, go for it.
Burning, extreme danger, clear the air.
He drops his megaphone, hides in the frame.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, frankium. But for some reason, they wouldn't let us have any of that. So there you go. Today's lesson.
Never mixed alkali metals with water.
The dogs. I didn't write it. But you get the idea.
If you give the thing core notation for the alkaline earth, they're all core notation NS2, N being the valence shell, okay? So, for example, beryllium, right next to lithium would be helium 2s2, magnesium, neon 3s2, same. Another group we've identified, and we did this in grade 10, are the halogens. Halogens are still a main group or representative group element. They all have 7 valence electrons. So their core notation, NS2, NP5, right? 7 valence electrons, same as the number of letters in the word halogen. And if we go to noble gases, except for helium, they're all NS2, NP6. So they have a completely filled valence shell. But it's not just 8, it's 2 in the S, 6 in the P. Okay. Now that fits into what you should be studying, because you need to remember core notation. You need to be able to write short form configuration. Now ions as well, but my point is we're not spending time on stuff that at this point isn't part of what you're already studying. So here we have oxygen as an element, calcium as an element, arsenic and cesium. This is core notation. Nearest noble gas to oxygen is neon. That's also the electron configuration, not just of neon, but of the stable ion of oxygen. So neon's configuration is helium 2s2 TP6. That's the same as the oxide atom. The nearest noble gas to this is this. They have the same electron configuration. The nearest noble gas to this is this. They have the same electron configuration. Arsenic loses 3 electrons, or arsenic gains 3 electrons to be just like krypton. And cesium loses 1 to be just like xenon. That's the whole point. So in other words, these stable ions are isoelectronic with the nearest noble gas. And remember, what we put inside those square brackets is everything except the biggest electrons, the biggest particles. Okay. Now this is the order of the fills. But the littlest, the biggest, it's 4d10, 5s2, 5d6. Now, why don't we just write? Why don't we not just write 5s2, 5d6? Can we be there? Because that's not really a coelectron. It's not part of the noble gas we just passed. And the fourth energy level isn't filled. Okay? So whenever we write co-notation, we go to the end of the previous period, put that noble gas symbol in square brackets. Then we write what comes after that, beginning with the next period at the alkali metals, right? Now, transition elements, we don't usually didn't separate those out into science 10. And I hate to write this in a book, but an explanation of the transition metals chemical behavior is beyond the scope of this course. In its entirety, it is, yes. But if we understand the basics of quantum mechanics, we can still understand why their chemical behavior differs from the main group elements. In the main group elements, the S and the P, where we're adding electrons are on the outside. That means that oxygen doesn't behave like fluorine, and fluorine doesn't behave like neon, because what's on the outside is different. For the transition metals, there are similarities within a period, in addition to similarities within a group. It's always true that elements in the same family have the same number of valence electrons. But with several members of the transition metal periods, the elements in the same period have the same number of valence electrons as well. So, case in point, member of the transition metal, for the most part, where we're adding the electrons is not on the outside, it's on the inside. And you can see that if you write them smallest to biggest. So scandium, what's on the outside? 4s2. Titanium, what's on the outside? 4s2. Vanadium, 4s2. Chromium is an exception, 4s1. Manganese, 4s2. Iron, 4s2. Gold, 4s2. Nickel, 4s2. Zinc, 4s2. Technically, they have the same number of electrons on the outside. So we shouldn't be too surprised that they're showing similar chemical behavior this way in addition to this one. Now, does that mean they react exactly the same? No, because where are the electrons going? They're not going on the outside, but they're going between the outer electrons and the nucleus. So we're stuffing electrons in a cloud close to the nucleus. That affects the chemistry, because the more electrons we put there, the more negative charge there is in the way of what's on the outside. And we're going to see that play out in periodic trends when we get to section 6.2. But we don't see similar chemical behavior left to right in the main group elements, but we do in the transition metals. And if you understand quantum mechanics, you can see why. So the differences mainly occur because the last electrons added for transition metals, that is the ones in the highest energy level, are placed in inner d orbitals rather than on the outside. Electrons in these orbitals are usually closer to the nucleus than the outer S and P ones filled for the representative elements. This quick check's easy. Yeah, none of these quick check questions are difficult. The reason I asked number 2 is because the most important thing to know about the periodic table is elements in the same family behave the same because they have similar outer electron arrangements. And if I gave you these formulas, you should be able to answer these questions. So if Based on this, what should the formula for sodium iodide be? Without looking at your periodic table. Potassium's in the same family as sodium, oxygen's in the same family. Or bromide's in the same family as iodine, so if this is 1 to 1, that should be 1 to 1. Barium sulfide. Barium is in the same family as calcium. Oxygen is in the same family as sulfur. So if the ratio of group 2 to a group 16 elements 1 to 1, it should be 1, and it is. Gallium's boron. Gallium isn't in your table, isn't it? Gallium's in the same family as aluminum. Fluorine is in the same family as chlorine. So this is 1 to 3, so will this one. Rubidium sulfide. Rubidium is an alkali metal. Just like potassium, sulfur is in the same family as oxygen, so this is 3 to 1, so is that. That's the point, okay? Now, quantum mechanical view of the periodic table. Let's look at a little more closely at the organization of the table from a quantum mechanics perspective. First, we'll look at 3 different aspects of the elements in the periodic table. Figure 613 showing the chemical family separated into the 4 main blocks, which we've done for you in the back of the book. Notice that each block corresponds to one of the 4 different electron sublevels, S, P, P, and N. Notice also that the number of columns or families in each block exactly matches the number of electrons that occupy that sublevel. So the S has 2 spaces because the S only has room for 2 electrons. The P block has 6 spaces because the P orbitals can accommodate 6. 10 for the D, 14 for the N. Sometimes my touch screen works, other times it doesn't. Consider in figure 613 the sublevels associated with each of the chemical periods in the table. Notice that as we read the sublevels left to right, like the words on a page, we follow exactly the order of filling orbitals specified by the Aufbau principle and summarized by that diagonal diagram. So if you drew with your ruler the diagonal diagram, as you are likely are going to do when you get to the test.
Afternoon, staff and students. In Tyler Long, please come to the main office.
Yes.
Now, as a faith and learning community, let us prepare ourselves for the end of day prayer. In the name of the Father, Son, and the Holy Spirit. Dear God, today let us reflect on our relationship with you. We know that you are the way to peace and happiness, yet it is often difficult to take time to discover the way to you. Help each of us make this a priority in our lives and recognize that the better we come to know you and accept you, the more happiness and peace our lives will hold. Amen. St. Thomas More, Blessed Edmund Rice, live Jesus in our hearts. In the name of the Father, the Son, and the Holy Spirit.
So I'm going to continue this on Wednesday, which is when I see you next. I'll probably get into section 6.2, but I'd like you to read to the end of 6.1, which is a couple of pages. It's also written very well. Have a look at the review questions. We'll probably get through a chunk of 6.2, but none of 6.2 is going to be on the test. Okay? 6.1 kind of applies, but not really 6.2. And then the test then is on Friday. And you're going to be where? Playing soccer on Friday?
Yeah.
Thursday, we have a late start because of a staff meeting. So instead of missing another block, instead of coming to a different block on Friday,
Yeah.
what if you came in at 8 o'clock on Thursday? Can you do that? Can you go here at 8?
I think so, yeah.
Okay, and then it's a 75-minute block recording.